because I will not be here a week from Friday. I will be at a safety summit.
Will that be exclusively chapter 3, or will there?
Well, we're going to start chapter 4 on Wednesday, so there will be part of chapter 4 on it. No. But I think chapter 4, if I remember right, chapter 4 is like the longest chapter. I don't remember. One of these chapters we're about to hit. I thought it was chapter 3. And then I went, nope, can't be chapter 3 because we're already done with chapter 3. So one of these chapters is fairly lengthy, and I just don't remember which one it is. Okay. I hate these configurations of these words.
That's odd that they don't accept that thermo class, because that one is pretty brutal.
The reason is it's a historic thing. UCO doesn't accept it because UCO used to be only a physics-only department, and thermodynamics and physics is a junior level course. So, and actually you will find that some institutions do 2 thermodynamics courses in their engineering program. They do the one that's equivalent to what we do as a sophomore, and then they do either a junior or senior level thermodynamics class, particularly if you're going into chemical engineering. You'll end up like with 2 or 3 thermodynamics classes. You end up with a graduate one. So I mean, thermodynamics is like that is a big part of chemical engineering. Sorry, guys. But it's an artifact of history that the engineering program at UCO is a 3,000 level thermodynamics course, because they still graduate a number of physics majors, and there is no 2,000 level thermodynamics for a physics major. So that's the fundamental reasoning behind it, and it works.
I don't know how much harder they can make it. That's pretty brutal.
Thermodynamics is fun.
It was fun. It was.
Yeah, thermodynamics is fun. Thermodynamics is all about boundary conditions. It's all about boundary conditions, and the boundary conditions get more and more fun as you get into processes. Yeah, so it's all about boundary conditions. All right, so the next section in this chapter is 3 dimensions. So, I mean, there's no more theory than what we already have, right? There's no more theory. It's the summation of forces in the x direction, summation of forces in the y direction, summation of forces in the z direction. No additional theory for what we're doing. So I figured what we'll do is we'll work some problems. The review problems will come up. But I wanted to start with one that looks like this. So this is a practical problem. We're going to knock down a tree, right? But initially we're going to be in equilibrium. So we've got a pulley that's in the system. We've got the rope that's there, and we know that the tension being pulled on, at least at this equilibrium point, is 60 pounds. We want to find the tension in the 2 ropes, and we want to find the angle between the 2 ropes. Okay? We want to find the tension in the 2 ropes. We want to find the angle in the 2 ropes. Well, there's a number of ways to work it. But, you know, one of the things that we did in the previous chapters was saying that sometimes it's better to change our coordinate system. And this is one of those cases where it's better to change our coordinate system. So this is going to be our x prime coordinate system, and this is the t on our 20-degree pull. Now, one of the things that you know that you don't think you know, that's a pulley. So if it's a pulley, what do we know about the tensions on the rope?
They're going to be the same.
They're going to be equal. So this T is going to equal that T. So TAC is going to equal TAD. So we can get rid of that part. And so I'm going to go ahead and put in our, wrong place, sorry. Because if I do this, this is 20 degrees, right? From my geometry, so my pull, one's gonna be down here, and this will be 10 degrees. And that will be our pull. So the pull is gonna be 60 pounds. Then we've got the other tension, which is someplace over here, and that has the angle between it. Okay? And then that gives us our Y prime. So we've got an X prime and a Y prime. We've just redrawn our picture, and now we can do summation of forces, right? So if my summation of forces in the X prime is going to be this, and this is going to be my positive side, so this is my 60 pounds cosine of 10 degrees. That's all in the X direction, so that makes life really nice. And then the other one is T cosine, and that all has to equal 0. Then the summation of forces in the Y direction is going to be negative 60 sine 10 degrees. And then it's going to be plus T sine angle is equal to 0. Two equations, two unknowns. So I end up with 60 cosine 10 degrees is equal to T1 plus cosine of the angle. And then I've got 60 sine 10 degrees is equal to T sine of the angle. So I can do one of two things, okay? I can do one of two things. One is I can use, I can solve for T, put that in there. I can go that direction. Or I can use a trigonomic identity, okay? So let's go ahead and do the solve for T, see what we get, right? I'm going to go ahead and calculate the 60 cosine 10 and calculate the 60 sine 10. So this is 59.1 is equal to T1 plus cosine of the angle. And 60 sine 10 is 10.4 T sine of the angle. So 10.4 divided by sine of the angle is equal to T. And then we get 59.1 is equal to 10.4 sine of the angle 1 plus cosine of the angle. And it looks like no matter what we do, we're going to have to use a trigonometric identity. And the trigonometric identity that the author uses is 1 plus cosine of the angle is equal to 2 cosine squared theta over 2. And you can play with whichever trigonometric identity you want to use to get there, but that's what the author used. And then also used, so for that one, used that one. And for this one, they went ahead and did sine theta over 2, cosine theta over 2, 2. So I get 59.1 is equal to 2t cosine squared theta over 2. And then I have 10.4 is equal to 2t sine theta over 2 cosine theta over 2. And I'm going to go ahead and put these back in. 60 cosine 10 degrees, 60 sine 10 degrees. I'm going to rewrite it 60 cosine 10 degrees. Two t cosine squared theta over 2. Now you see why the author does it the way he does it. Because one of these cosines goes away, I end up with the tangent of 10 degrees is equal to the tangent of theta over 2. Theta ends up being 20 degrees. And then t ends up being 10.4 divided by sine 20 degrees, which should be equal to about 30.5 pounds.
Dr. Woodlock,
Yeah.
for some reason Enid's got a visual of another classroom.
Okay.
There we go, thank you. Give us a moment. Oh, you got it? Okay, thank you.
Ah. Were you seeing Kyle instead of the?
Yes.
Yeah, for a little bit.
For a moment.
Okay. Well, that's a first. That's all right.
How would you solve for theta if tangent 10 degrees is equal to tangent of theta over 2?
Figure out what tangent of 10 degrees is and do the inverse tangent.
Oh, okay, yeah.
That's how I do it.
I was looking at it there and I was like, inverse tangent of 10 degrees equals inverse tangent of
But then again, you can also do it by inspection.
just plugging a number.
Well, no, look. If 10 degrees is here, theta over 2 has to equal 10 degrees.
Okay, yeah. So then it'd be 20.
Yeah.
Okay.
So you can do that one by inspection. So the trick to this one is getting those trigonometric identities out. And remember, you have a bunch of them in the appendix of your book. All right. So we're gonna do this one next. We got a pot. It's in 3 dimensions. And you will find that's the way this book works. We do everything in 2 dimensions first, then we do 3 dimensions. Because 3 dimensions gets a little harder to picture. So we're told that the flower pot is 25 kilograms. And it's supported by the 3 chords, and we want to determine the force acting in each chord. So the big problem with this one is writing down the 3 vectors. I mean, that's fundamentally the issue with this problem, is writing down the three vectors. And it's looking at what the pictures are telling us for the 3 vectors. So one of the things is let's look at the vector for a second. Vector AB is just in the y direction and in the k direction. So AB is just in the y direction and the k direction. That's going to make life easier. So let's go ahead and write that one down, because life is going to be good. If we can write that one down, that's even better. So FAB is going to be FAB, and it's going to be sine of 45 degrees in the j direction plus FAB cosine 45 degrees in the k direction. And just for grins and giggles and practice, UAB is going to be sine 45J plus cosine 45K, just for practice. Okay, we don't necessarily have to use that for anything in this one, but that's just for practice, and we know, and by the end of the semester, you should remember that sine is or cosine of 45 degrees and sine of 45 degrees is this right here. I mean, we get used to that. So that's just for grins and giggles. Now the other two, not so much, because D and C are off of the XYZ plane, but if you look at them, they're going to be the same, just that one's going to be in the negative direction in the X direction, and one's going to be in the positive direction in the Y and the X direction, right? So if I do FAD, and this is one of those times you may want to go back and look at it, but FAD is going to be, because they've given it to us in these kind of coordinates, I'm going to get the sine of 30 degrees I. And when I'm looking at these tensions, I want to make sure I've got that. Okay, that one's going up, so that's good. This one's going there. FAD minus cosine 30 degrees sine 60 degrees J. And that's plus cosine 30 degrees cosine 60 degrees K. And the minus comes because we're setting this as the origin. Right? The minus comes because we're setting that spot as the origin, even though the picture's not drawn that way. And then FAC is going to look a lot like FAD, except FAC is going to be minus sine 30 degrees I minus cosine 30 degrees sine 60 degrees J, and then we get plus cosine 30 degrees cosine 60 degrees K. So we're going to rewrite these. So FAB is equal to FAB 0.7071 J plus 0.7071 FAB K. FAD ends up being 0.5 FADI minus 0.75 FADJ plus 0.433K, and FAC minus 0.5 FACI minus 0.75 FACJ plus 0.433K. And then we have the weight is equal to 0.25 or point, that's not, it's 25 times 9.8, and that is negative in the Z direction for the picture. Okay, it's negative in the Z direction for the picture. If you go picture there, that way. So now you just do the summation of forces. Summation of forces in X, 0.5 FAD minus 0.5 FAC has got to equal 0. FAD has got to equal FAC. That's gonna be helpful.
Oh, no, there was no.
There's no I in it. There's nothing in the X direction on that one. And so that's also when you start looking at these problems, if you're given a problem that's not like the book problem, pick your coordinate points, because it's gonna help you out. So now we do summation of forces in the y direction's gotta equal 0. And in this case, we've got FAB 0.7071 minus 0.75 FAD minus 0.75 FAC, but we know FAD and FAC are the same, and we have a minus, and that works out to be 242.25, 25 times 9.8. No, that's in the K direction, never mind, we're in the Y direction. So I get 0.7071 FAB is equal to, or minus 1.5 FAC, just for grins. 0.7071 FAB equals 1.5 FAC. FAB is equal to 1.5 FAC divided by 0.7071. Now we do the K1. And that's 0.7071 FAB plus 2.433 FAC. Because it's easy, we can go ahead and do that. Everybody see that I got two of those right there? And we know AD and AC are the same. So I just shortcutted a step. That's minus 242 or 245.25. We know what FAB is.
Can you scroll it up? Yes. Thank you.
We know what FAB is, so we can plug in for that. That's nice. That makes it nice. FAC is equal to 245.25 divided by 1.5. What did I do wrong? Oh, forgot that part right there. Oh, wait a second, something's not right. We left out a term. So we get 24525, 1.5 plus 0.866 FAC. We get 245.25 divided by 2.366 gives me 103.6, which is approximately 104. Then we can plug it back into that one. 1.5 times 104 divided by 0.7071 gives us FAC is equal to 220. And those are both in newtons.
Seems like the hardest part is just keeping track of the negatives and the directions.
The hardest part is getting the unit vectors. Fundamentally, the hardest part is getting the unit vectors.
And you're trying to read the picture.
And yeah, that's it.
That's pretty hard.
And that's fundamentally it, because if you look at this one, we got a traffic light. Okay? So we got a traffic light. That's why I said, when in doubt on these things, draw your force diagrams, okay? That's first thing, draw your force diagrams. And then the next part is draw your unit vectors. So for this one, we're going to take H, given H that's in the middle, is going to be 4 meters. And we want to determine the tension in the cables if the traffic light is 15 kilograms.
That seems like it's a light traffic light.
Well, traffic lights aren't all that heavy.
I was expecting like 100 pounds or something.
No, they're not all that heavy. So the first thing you want to do is find the unit vectors. So we're going to do AB, okay? We're going to do AB. So what we've got for AB is we know that this is my X direction, okay? We're going to be at the center here. So how am I going to do this? You know that's. How do I do this? I do AB. Okay, if we make this my origin, okay, so there's my origin there. These are at 4, okay? These are at 4 and C is at 6. So that's one of the things that we've got to do. If I make that my origin, RAB has got a 0 in the K. Everybody okay with that? If I make this my origin, these are 4 meters, 4 meters, this one's 6 meters. And if I have that as my origin, that's going to have a 0K. We're not going up or down in the K direction. When I do RAC, it's going to have +2 in the K direction. And RAD is going to have 0 in the K direction from my picture, if H is equal to 4. I don't have any, and we're given the problem that H is equal to 4. So I don't have anything in the K directions. Now all R is a position vector in my space. So if I do that, then I have 3 in the I direction, because there's my 3 in the I direction, and I have 4 in the J direction. For RAC, I end up with -6 in the I direction, and I end up with -3 in the J direction. And then for RAD, I end up with -3 in the I direction, and I end up with a +4 in the J direction. So now what I want to do is I want to find the magnitude of RAB. That's the square root of 9 plus 16 equals, did I do that right?
Should be.
9 plus 16, 25 equals 5. So UAB is equal to 3/5 I plus 4/5 J. Magnitude of RAC, square root of 36 plus 9 plus 4 is equal to 49, which is equal to 7. So UAC is -6/7 I, -3/7 J, plus 2/7 K. That one's 5 again, so that makes life a lot easier. We just have to go in and do it, except that's -3 in the I direction plus 4 in the J direction. So now I've got my unit vectors. And now you just plug in your forces. So my force vector AB is force AB, UAB, which means it's 3FAB fifths in the I, plus 4FAB fifths in the J. And we do the same for each one. And I'll give you the answers so that you guys can work it through yourself. FAB is equal to 441 newtons. FAC is equal to 515 newtons. And FAD is equal to 221 newtons. Again, fairly straightforward. The tough part is finding the unit vector. Tough part's going to be finding the unit vector for each of those vectors.
Would we figure the tension by starting with the weight of the traffic light and then
Yeah,
just-
because you've got, these are the 3 cables here, but you do have the weight of the traffic light going down.
And we don't have any of the tensions in the cables.
We don't have any of the tensions in the cables, but you know that that's 15
Yeah.
kilograms. So you do some of your components in the X direction, some of the components in the Y direction, which means you have 3 equations, 3 unknowns. Now remember, there's a couple of ways to do 3 equations, 3 unknowns. Right? You can do 3 equations, 3 unknowns. Remember, there's the determinant method. So if I have, because some of these are not going to be nice and neat with just 3. 3 you can work through and do it algebraically, right? 3 we can do it algebraically, but if I have AI plus BJ plus CK is equal to some value D. And I'm going to do the 1, 1, 1, 1 thing. And I have the A2I plus B2J plus C2K is equal to D2. And A3I plus B3J plus C3K is equal to D3. And remember, we could have done this, and I'm going to do it. I'm going to go in here and give it to you algebraically. So if this is X, Y, or X, X, Y, 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 Z, 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 we get this matrix, A1, A2, A3, B1, B2, B3, C1, C2, C3. And if I want to solve for one of these, remember what I end up doing. If I'm wanting to solve for A or for the X component, what I do is I do D1, D2, D3, B1, B2, B3, C1, C2, C3, divided by this puppy in the bottom. Remember that? Last place we saw that was when we were solving loop equations in Physics 2. So if I get to multiple equations, for this one, for these, doing 3 equations, 3 unknowns, not a big deal. We can do the substitution, we go in, but if we start adding more and more vectors, we're probably going to have to move to the matrix system like this in order to solve it. This is called the determinant method. And when you guys get into circuits, you're going to want the determinant method. So for those of you who have to take circuits, that's going to be one of the bigger tools in your toolbox. Okay, are we good? This all making sense? Okay.
So where do you find the solutions for those?
What?
In the book?
I gave them to you.
Yeah, it's just in the back of the book.
Because I'm not finding, I'm only finding like 2.
It's like indices
Well,
or something
yeah,
like
it's in the
that.
appendices. You get solutions. This is a problem. Now they only give you selected problems. They always give you the review problems. They give you the fundamental problems.
Yeah, not all of them, it's just.
Yeah, they don't give you all of the other problems. They give you just selected.
But that one you just showed us had all of them, the whole thing on there. 'Cause
It did?
Because it's your teacher edition?
Yeah.
So are we gonna be able to get a hold of some of yours or like notes or?
No. I wrote it out.
So can I buy the teacher?
No, but you have in the back of the chapter, all the review problems have their solutions.
Yeah, they have all the answers.
No, the review problems actually have the solutions.
Does-
Remember, you have fundamental problems, you have preliminary problems, you have review problems. The other ones just give you the answers. But the review problems actually give you the solutions.
These are pretty short.
They're pretty short, yeah, they are. They don't necessarily give you every step. But even look at this one. So this is this one. That's basically what it gives you in the back of the book. It just gives you the unit vectors, the sums, it doesn't solve it for you.
Yeah, they leave the algebra to you.
They leave that, yeah, they always are gonna leave the algebra to you.
Don't the fundamentals, like some of them, don't they have the,
Some of the fundamentals, they do show the algebra, because like this one, the one that we did here, this one was trickier because we did the solutions with the sign ones. They actually gave you more of the inner step. But this is a back of the book problem.
What was the problem number for the hanging plant one?
The hanging plant one, the one I did was problem 56. The one you have in your homework is problem 57.
Okay. I'm just trying to write these down so Kayla knows which
Yeah,
ones to
yeah.
look at.
And the tree problem is 3-7, and the traffic light problem is 358.
Thank you.
Okay? All righty, we're gonna call it a day. We start chapter 4. And so what you've got homework-wise is